Welcome dear learners. We are continuing Unit 4 Fundamentals of Analytical Chemistry. In the present module, we are discussing precipitation and complexometric titrations. The contents of this module are precipitation titration, adsorption indicators, selected examples for precipitation titration, complexometric titrations, complexometric indicators, and selected examples for complexometric titrations. First of all, we are dealing with precipitation titration. We heard about volumetric analysis. Volumetric analysis is a quantitative chemical analysis in which we are finding out the concentration of an analyte by measuring the volume. There are several types of titrations in volumetric analysis. These include acid-base titration, redox titration, precipitation titration, complexometric titration, etc. The present module is intended to discuss two types of titrations. They are precipitation titration and complexometric titration, out of which we are focusing on precipitation titration in this part. So, precipitation titrations are a type of volumetric analysis where the reaction between the analyte and a reactant or a titrant results in the formulation or formation of a precipitate. So, the precipitation titration is a titration in volumetric analysis and it involves the formation of a precipitate. These are especially useful, these kind of titration are especially useful for determining the concentration of ions that form sparingly soluble salts with specific titrants. For example, Ag plus is a cation which can form a sparingly soluble precipitate of AgCl with Cl minus ion. It can also form other precipitate AgBr with Br minus ion. So, in the precipitation titration, there do occur the formation of at least one sparingly soluble precipitate or sparingly soluble salt. Now, the principle of precipitation titration is here. A soluble reagent, that is the titrant, is added to a solution containing the analyte ion. When these two react together to form an insoluble compound, the end point of the titration corresponds to the completion of the reaction. A common example or a common type reaction in precipitation titration is shown here. It is the reaction between Ag plus and Cl minus to produce the precipitate of AgCl. You are familiar with the AgCl precipitate, which is a white KD precipitate soluble in NH4OH. Since it is a precipitate, it is sparingly soluble or practically insoluble in water. You have a solution containing Cl minus ion. In order to estimate the amount of Cl minus ion present in that sample, you can add Ag plus ions in the form of AgNO3, and the Cl minus present in the solution is precipitated as AgCl, and the end point can be determined by a kind of indicators called adsorption indicators. We will discuss more about adsorption indicators in the coming slides. So, by this procedure, you can estimate the presence of Cl minus ions present in the given solution. And in a similar way, you can also estimate the amount of Ag plus present in a given solution by adding the Cl minus ions in the form of HCl or sodium chloride like that. So, you can quantitatively convert the Ag plus ions present in the solution to AgCl precipitate. And if there is an endpoint which indicate the completion of the reaction can be identified with the help of a category of indicators called adsorption indicators. So, on a sum, in a nutshell, you can say that the precipitation titration involves the formation of a precipitate between two reactants, out of which one is titrant and the next one is analyte. Now, we are discussing about indicators used in precipitation titration. Since no color change naturally accompanies the precipitation. A special kind of indicators are used to identify the end point in a precipitation titration. The most common category of indicators used in precipitation titration are adsorption indicators, which change color when they adsorb onto the precipitate surface after the equivalent point or end point. That is, similar to other type of indicators, adsorption indicators shows a color change during their adsorption onto the surface of a precipitate after the end point or theoretically the equivalent point. Now, we can enter into the details about, more details about the category of indicators used in precipitation titration, that is nothing but adsorption indicators. Adsorption indicators are special dyes, they are organic dyes, they can produce some color, they contain some chromophore, or adsorption indicators are special dyes used in precipitation titrations, particularly for halide ions like Cl minus, Br minus, etc., where the end point is detected by a color change due to adsorption onto the precipitate. Suppose you imagine the situation, you are estimating Cl minus ions or Br minus ions present in a given sample solution by adding the titrant AgNO3. In this situation, you are precipitating Cl minus as AgCl or Br minus as AgBr. In this circumstance, at the end point, adsorption of this indicator on the surface of the precipitate occurs, and that specific adsorption leads to a color change. So, you can identify the end point in a precipitation reaction by using a category of dyes. They are nothing but adsorption indicators. They shows the color change because of the specific adsorption of that indicator onto the surface of the precipitate during the completion of the reaction or at the equivalent or end point of the reaction. Now, we are discussing the working of adsorption indicators, that is the working principle, how this indicator, adsorption indicator works. During the titration, for instance, Cl minus with AgNO3, silver ions react with chloride ions to form a white cloudy precipitate, that is AgCl precipitate. Before the equivalence point, the precipitate surface is negatively charged. Why this negative charge on the surface of AgCl precipitate? This is specifically due to excess of Cl minus ions which are attached to the AgCl surface. So, before the end point of the reaction between Cl minus with the Ag plus ions, the obtained AgCl precipitate is negatively charged due to the presence of Cl minus ions present in the medium. Now we have to think what happened at the end point or after the end point. It is clear that all the Cl minus ions are converted to AgCl at the end point. So, at the end point or equivalence point, what is the difference between end point and equivalent point is that equivalent point is the theoretical point at which the reaction completes, and end point is the indication of the equivalent point. So, what I am saying is that at the equivalent point, there will not be any Cl minus ions present in the medium. This is because all Cl minus ions are converted to AgCl precipitate. Suppose after the end point, if you are adding very small quantity of Ag plus ions, then that Ag plus ions will be in excess, and after the equivalent point, the precipitate will be changed to positively charged precipitate. Prior to the end point, the precipitate is negatively charged due to the presence of excess of Cl minus ion. At the equivalent point, all the Cl minus ions are consumed, and with the slight excess of Ag plus ions, the surface become positively charged. So, you have to keep in mind, Whenever you are estimating Cl minus ions by adding Ag plus ions, prior to the end point, the precipitate AgCl will be negatively charged due to the presence of Cl minus ions present in the medium, and after the end point, this negative charge on the precipitate is changed to positive charge, and this positive charge is due to the presence of excess of Ag plus ions from the titrant. So, the precipitate is now after the end point is positively charged. The anionic dye means the anionic part of the organic dye, that is the adsorption indicator, then adsorb onto the positively charged surface and undergoes a visible color change. You imagine you are using an adsorption indicator which is a dye which is having an anionic part. This anionic part selectively adsorbs on the surface of the positively charged precipitate, and this positive charge will be generated only after the end point. So, close to the end point, this negatively charged part of the indicator adsorbed on the surface of the positively charged precipitate, and this leads to generation of a visible color, or there occur a color change, and this color change is used to identify the end point of the reaction. Now, we are discussing popular adsorption indicators. I already mentioned the fact that adsorption indicators are a category of indicators used in precipitation titration. They shows a color change owing to their selective adsorption onto the surface of a precipitate at the end point, or after the end point, or very close to the end point. This color change made easy the detection of the end point in the precipitation titration. So, now we are focusing on the popular adsorption indicators. This is a chart that depicts common adsorption indicators which are very popular in precipitation titration. The first column stands for indicators, second column represents color before the end point, and color after the end point is also here. Typical use is also shown in the last column. The first indicator is an organic dye, that is nothing but fluorescein. Fluorescein is having yellow-green color prior to the end point, but at the end point the color is changed to pink, and it is specifically used for the Cl minus ion titrations. Another one is eosin. This is also a dye compound which is yellowish in color prior to the end point, and at the end point the color changes from yellowish to pink. This is specifically used in titration involving Br minus ions. Now, dichlorofluorescein is a derivative of the first dye, that is fluorescein. It is having pale yellow color prior to the end point of the reaction. At the end point, or immediately after the end point, the color changed to pink red, and this color change from pale yellow to pink red enable the detection of the end point using dichlorofluorescein as the dye, and this dye is highly useful in titrations involving precipitation titrations involving Cl minus and Br minus ions. So, this about popular adsorption indicators. You have to remember the names. These include fluorescein, eosin, dichlorofluorescein, etc. Now, we are focusing on some selected examples of precipitation titration. We learned the concept of precipitation titration. We understand the working of a category of indicators used in precipitation titration, that is nothing but adsorption indicators, and now we are looking on some selected examples for the precipitation titration. And this first method is a named method. It is nothing but Morse method. This method, this Morse method, is used for estimation of chloride ions present in a given solution. And in this Morse method, the titrant used is standard silver nitrate. And indicator used for this reaction is a specific reagent. Remember, this is not an organic dye. This is a compound. This compound is potassium chromate with the molecular formula K2CrO4. Potassium dichromate is K2Cr2O7, and this indicator used for the Morse method is potassium chromate, and its molecular formula is K2CrO4. End point is indicated by the formation of red, brown, silver chromate with the molecular formula Ag2CrO4 after all Cl minus ions has precipitated as AgCl. So in Morse method, you can have a solution of Cl minus ion to which you are quantitatively add Ag plus ions as AgNO3 and indicator used is potassium chromate. At the end point, you can note a color change and the formation of red brown color indicates the end point in the reaction, and this red brown color is owing to the formation of the substance Ag2CrO4, that is nothing but silver chromate. Now another method in precipitation titration is here. This method is called Olhard's method. This method is a back titration method, and this method is specifically used for the estimation of the halide ions, preferably Cl minus, Br minus or I minus. Here also the titrant is AgNO3, and this AgNO3 should be added in excess during the course of the reaction. This is a back titration. Excess Ag plus is titrated with thiocyanate ion, that is SCN minus ion, and the indicator used for this reaction is some ferric ion, Fe3 plus ion. That Fe3 plus ion forms a reddish color due to the formation of FeSCN2 plus. Now another method of precipitation titration is here. This is Fajan's method. This method is used for estimation of halide ions. Here also the titrant is AgNO3 and the indicator is adsorption indicator like fluorescein. End point is the color change when indicator is adsorbed on the precipitate after equivalent point. So this method by these contents is known as the Fajan's method, and this Fajan's method is very important precipitation method, especially used for the estimation of halide ions. So we heard about 3 important selected precipitation titration methods. So the Fajan's method deals with the estimation of halide ions. In all the 3 methods we have studied, the titrant is AgNO3, and in all the 3 cases we dealt with the estimation of halide ion, chloride, bromide or iodide ion. Now we are entering into another part of this module, that is nothing but complexometric titrations. We learned the fact that there are several kind of titrations used in volumetric analysis that include acid-base titrations, redox titrations. Now we studied about precipitation titrations, and there is one more important category that we are discussing now. It is nothing but complexometric titrations. The reactions involving complex ions or undissociated neutral molecules falls under the category of complexometric titrations. You are familiar with the coordination complexes. What is a coordination complex? In a coordination complex, there are 2 essential parts. There should be a central metal ion and there are some ligands. The coordination complexes are formed by the coordinate bond between the ligand and the central metal ion. Ligand acts as electron donor. A ligand that can donate a pair of electrons is said to be monodentate ligand. There are bidentate, tridentate and polydentate ligand. There occur the formation of the coordinate bond between the central metal atom or ion and the ligands present in the medium. So there are a category of compounds called coordination complexes, and also you learn the very basic things associated with the coordination chemistry and coordination compounds in your +2 classes. So this complexometric titration involves the formation of complex ions or undissociated molecules. These titrations involve complexation, that is coordination complex formation, using monodentate, bidentate or multidentate or simply polydentate ligands. That is, the complexation happens between the ligand and the central metal atom or ion. It should be noted that the ligand may be monodentate, which can donate a pair of electron, a bidentate ligand which can donate 2 pair of electron, or a polydentate ligand like ethylene diamine tetraacetic acid. There you can donate many pairs of electrons. So, this complexometric titration invariably deals with the complex formation between the central metal atom or ion and some category of ligands. A simple example is of the complexometric titration is the reaction or titration between cyanide ions with AgNO3 solution. It is very well clear that Ag plus ion can act as a central metal atom or ion, and Cn minus or cyanide ion is an excellent ligand. It is a powerful ligand also. So, when AgNO3 is added to a solution containing cyanide ions, there do occur the formation of a white precipitate. And on stirring this precipitate, on continuous stirring, the obtained precipitate of AgCN dissolves in solution owing to the formation of a new complex cyanide with the molecular formula AgCN twice minus charge, and this is indicated by the reaction Ag plus ion plus 2Cn minus ion reversibly produces AgCN twice minus. Remember, whenever you are adding some Cn minus ions to a solution of Ag plus, then immediately there occur the formation of a white precipitate of AgCN, silver cyanide. You have to continue the addition. Then the white precipitate of AgCN dissolves and a new complex ion, namely AgCN twice minus, is produced. This reaction is a selective typical example for a complexometric titration. Now, when the above reaction is complete, further addition of AgNO3 solution yields an insoluble silver cyano-argentate complex, that is AgCN twice 2 minus. This point I already mentioned. This type of complexation can also be used for the determination of several metals, preferably nickel, cobalt, zinc, etc. So, this about the very basic principle of the complexometric titration. However, the metal ion determination can be made more convenient with the help of the polydentate ligand EDTA, and EDTA stands for ethylene diamine tetraacetic acid. Theoretically speaking, ethylene diamine tetraacetic acid is a hexadentate ligand. A ligand which can donate a pair of electron is said to be monodentate. If it is able to donate 2 pair, it can call it as bidentate. If it is able to donate 3 pair, it will be a tridentate ligand. In a similar way, a polydentate ligand can donate many pair of electron, and specifically EDTA or ethylene diamine tetraacetic acid is a polydentate ligand with its maximum density equal to 6. Actually, EDTA is a hexadentate ligand. It can donate 6 electron pairs in maximum. This is mainly attributed to the significance of EDTA is mainly attributed to the fact that ethylene diamine tetraacetic acid or EDTA can form soluble complexes, soluble coordination complexes with many metal ions of analytical significance. For example, zinc ions can be titrated with EDTA, magnesium ions, nickel ions, cobalt ions, calcium ions. There are so many metal ions that can be estimated using complexation with the help of ethylene diamine tetraacetic acid. So remember, ethylene diamine tetraacetic acid is an inevitable reagent in complexometric titration. Now, we are looking into the structure and more details about the hexadentate ligand ethylene diamine tetraacetic acid. The non-polar structure of ethylene diamine tetraacetic acid can be shown or can be represented like this. The name of this molecule is ethylene diamine tetraacetic acid. So you have to represent the molecule ethylene diamine first. What is ethylene diamine? CH2 single bond CH2, NH2, I am putting another NH2. This molecule is abbreviated as EN, or it is otherwise called ethylene diamine. Now what will be the structure of ethylene diamine tetraacetic acid? Here you can see the presence of two NH2 groups in ethylene diamine molecules. And I have to replace these two hydrogen with the two acetic acid molecules. Again, here also two hydrogen atom, that is also replaceable with the two acetic acid molecules. Therefore, I have to incorporate four acetic acid molecules in this ethylene diamine. Then I will get ethylene diamine tetraacetic acid. So, the non-polar structure, the structure without charge separation of ethylene diamine tetraacetic acid is obtained by incorporating four acetic acid molecules into this structure of ethylene diamine. That's why it is possible to represent the structure of EDTA like this. I am simply representing the center part, that is ethylene diamine part. Here there is one nitrogen. Two hydrogen atoms are already present. I just replace it with the two acetic acid molecule part. Then I am putting CH2COOH. Remember, CH3COOH is acetic acid. In order to inculcate it on the nitrogen atom, I have to replace one hydrogen from acetic acid also to maintain the valency, to maintain the tetracovalency of carbon. So one acetic acid molecule is introduced here. The second acetic acid part is CH2COOH. In a similar way, you have to put two acetic acid molecule part on left hand side also. Here I am representing CH2COOH. This part also I am representing CH2COOH. So you can see the presence of four acetic acid molecules in an ethylene diamine. This represents the non-polar structure of ethylene diamine tetraacetic acid, which is an inevitable, most important complexing agent as far as the complexometric titrations are concerned. Now, EDTA is commonly available as disodium salt, which is represented by the formula Na2H2Y. So, this about some important matters associated with the ethylene diamine tetraacetic acid. Now, we are focusing on various types of EDTA titrations. You can deal with more important aspects of several kind of EDTA titrations in your higher classes. Now, we are mentioning about what are various types of EDTA titrations. There are four important EDTA titrations. There are four important types of EDTA titrations, and we can name that or we can identify that. And these four titrations are direct titration. The second category is called back titration. Next category is called replacement or substitution titration. And the last category is alkalimetric titration. Remember, these are four important categories of EDTA titrations. So, EDTA is a very important reagent in complexometric titration, and with the EDTA, you can have four different types of titrations. These four titrations are shown here. Now we are discussing complexometric indicators. It should be noted that in order to find out the end point of a reaction or end point of a titration, we must have some coloring agents, we must have some reagents, and these reagents help in identifying the end point, which is the indication of the equivalent point in a titration. Now we are focusing on complexometric indicators. As the name indicates, the complexometric indicators are the indicators used in complexometric titration. So, this is the definition. The indicators used in complexometric titration are called complexometric indicators. Complexometric indicators are also known as metallochromic indicators. Remember, this is a very important synonym of complexometric indicator. Complexometric indicators are otherwise called metallochromic indicators. And these metallochromic indicators are organic dyes used in complexometric titration to detect the presence of metal ions through a visible color change. So, this about the complexometric indicators. Moving on to more details of the complexometric indicators, we can say that the complexometric indicators are organic ligands that form colored complexes with the metal ions. When complexing agent like ethylene diamine tetracetic acid is added, it displays the indicator from the metal ion complex due to its strong binding, causing a distinct color change that signals the end point or equivalent point of the reaction. Now, we are discussing with the working of complexometric indicators. The metal ion, that may be calcium 2 plus, zinc 2 plus, magnesium 2 plus, etc., initially forms a weak complex with the indicator. That means you have to take the analyte solution, you have to add fixed quantity of the complexometric indicator, and this complexometric indicator forms weak complex with the metal ion present in the system. Now, during the titration, EDTA, which is a strong chelating ligand, is added first. EDTA binds more strongly to the metal ion and displaces the indicator. The indicator, now free in solution, returns to its original color, signaling the endpoint. Now, we can have a discussion on popular complexometric indicators. This is a chart that gives idea about different type of complexometric indicators. And the first column represents the indicator. Metal ion complex color is shown in the second column. Free indicator color is shown in the third column, and the last column represents the common metal ions that can be estimated with the help of the corresponding indicators. The first indicator is eriochrome black tea. It is otherwise called solochrome black tea. It is wine red in color during the formation of metal ion complex. The free indicator is blue in color. This is useful in estimating the metal ions magnesium 2 plus, calcium 2 plus, zinc 2 plus, etc. Another complexometric or metallochromic indicator is muroxide, and this muroxide is pink violet in its metal ion complex, and this is yellow in color when this indicator is free, or without the complexation the indicator will be yellow, and during complexation with the metal ion the color should be pink violet, and this is highly useful in estimating the presence of metal ions like calcium 2 plus. Now we are discussing some selected examples of complexometric titrations. The first one is estimation of zinc or Zn2 plus ions present in the solution. Our aim is to estimate the mass of zinc or zinc 2 plus ion in the whole of the given solution. Approximately 0.05 molar EDTA and annular zinc sulfate crystals are being supplied. You are having these two reagents, that is nothing but 0.05 molar EDTA and annular zinc sulfate. With the help of these materials, you have to estimate the presence of zinc ions or zinc 2 plus or simply zinc present in the given solution. Zinc sulfate crystal is used to prepare a standard solution with which EDTA can be standardized. So remember, this zinc sulfate is a primary standard. You can weigh it out and you can prepare a standard solution of zinc sulfate. That zinc sulfate solution can be titrated with EDTA to get the exact concentration of EDTA. This stage is called standardization of EDTA. Using this standardized EDTA, it is possible to estimate the zinc 2 plus or zinc ions present in the solution by titrating with the standard EDTA and the given zinc salt solution. Now, the principle is here. Zinc 2 plus forms complexes with EDTA according to the equation. Zn2 plus plus H2Y2 minus gives Zny2 minus plus 2H plus. The end point is detected by eriochrome black tea or solochrome black tea, which has a blue color in the pH range between 7 to 11. This indicator reacts with Zn2 plus ions to produce zinc eriochrome tea indicator complex, which has wine red color. During the titration with EDTA, the free zinc 2 plus ions react with EDTA to form zinc EDTA complex. After all the zinc 2 plus ions are converted into zinc EDTA complex, the addition of the next drop of EDTA causes the decomposition of zinc indicator complex and the free indicator liberated, which gives a blue color at the end point. Now, these are various steps we adopted during the estimation of zinc. First step is the preparation of standard zinc sulfate solution. And using this standard solution, it is possible to standardize the given EDTA solution. That is the second stage. And the third stage is the titration of standard solution of EDTA with the given zinc solution. That is the estimation of zinc. So, these about various steps in the estimation of zinc using complexometric titration with the EDTA. Now, we are focusing on estimation of magnesium. Instead of zinc 2 plus ion, now I am taking the estimation of magnesium as a representative example, as another representative example. Here the aim is to estimate the amount of Mg2 plus in the whole of the given solution. You are supplied with approximately 0.025 molar ethylene diamine tetracetic acid EDTA and annular magnesium sulfate. Magnesium sulfate crystal is used to prepare a standard solution since it is a primary standard which react with EDTA, and this enables the standardization of EDTA. The estimation is based on the reaction magnesium 2 plus plus H2Y2 minus gives MgY2 minus plus 2H plus. A standard solution of magnesium sulfate is prepared and the given EDTA solution is standardized using eriochrome black tea as the indicator. So, magnesium sulfate fixed quantity is weighed and prepared a standard solution. Using that standard solution, it is possible to standardize the given EDTA solution. Now, you are having standardized EDTA solution. This standardized EDTA solution can be titrated with the magnesium ions present in the sample. In the presence of metal ions, eriochrome black tea, that is nothing but EBT indicator, gives a wine red color in the pH range of 7 to 11. At the end point, all the metal ions are converted into metal EDTA complex and the free indicator is liberated, which has blue color. During the standardization or during using the standardized EDTA, Mg2 plus present in the given solution is estimated. Here also EBT, that is eriochrome black tea, is used as the indicator. Now, we are looking on to various steps as a consolidation that we adopted in the estimation of magnesium. This is the first step, preparation of a standard solution of magnesium sulfate. And using this magnesium sulfate solution, you are standardizing the given EDTA solution. That is, standardization of EDTA solution is the second step. The third step is the estimation of magnesium present in the given solution using standardized EDTA solution. That all about the present module on precipitation titration and complexometric titration. Have a nice learning experience. Thank you.